Hello, everyone, and I hope you're keeping well in this pandemic. And this is the Life in the Universe pandemic series. So, just a set of short talks about things to do with life in the universe that I think are interesting, and I hope you will as well. And even if it's not the pandemic, beyond the pandemic, hopefully these talks might be an interesting introduction to matters to do with life in the universe. So, today I want to talk about this topic that is very relevant to life in the universe. What are the limits to life? And this is a very important thing to understand. You might think, why do people care about the limits to life? Well, if you want to go to another planet like Mars or an exoplanet and to ask the question, could there be life there? It's useful to know what the limits of life, at least known life, are on the Earth, because then you can ask the question, do the conditions that I find on Mars or somewhere else overlap with conditions on the Earth that we know can support life? So to be able to assess other planetary bodies as possible places for life, you have to know where the boundaries of life are on our own planet. It also has practical implications if we're worried about climate change or the effects of human pollution on the Earth. It's useful to know how far you can push the biosphere before you push it over the edge. And to be able to do that, you have to know something about the limits of life. So the limits of life are an important thing to understand. And people have studied all sorts of extremes, life in extreme environments. I think this probably started in the 1950s and 60s, or at least one of the major studies in which this all began was studies done by Thomas Brock, who was a microbiologist, and he went off to Yellowstone National Park in the United States, where there are lots of volcanic pools bubbling and boiling away, and he looked at the microbes in those pools. And to his astonishment, he found microbes growing at 70 degrees. But when he investigated these even further, what he found is not only could these microbes tolerate 70 degrees, but they needed these temperatures to grow. If you brought them to temperatures that you and I feel comfortable with, 20, 30 degrees, not only did they stop growing, but they might even have died. So here we had life forms that were adapted, that required higher temperatures to grow. In the 1970s, hydrothermal vents were discovered, these vents gushing fluids from the Earth's crust into the oceans. And around these mounds of minerals in the deep oceans, people found microbes. And to their amazement, they found microbes that grew at temperatures above 100 degrees. So, of course, we are familiar with the fact that water boils at 100 degrees, but that's at 1 atmosphere. If you pressurize it, it will boil at higher temperatures. And microbes were found growing at these higher temperatures. In fact, today, the upper temperature limit for life is at 122 degrees Celsius, which is set by a microbe that was found in one of these hydrothermal vents. And of course, the upper temperature limit for life might go higher than that, but that's where it is at the moment. And what I find fascinating about the upper temperature limit for life is it really does define the extent of life on our planet. If you drill down into the Earth, the temperature increases because of the geothermal gradient, the primordial heat inside the Earth, and the heat from decaying radioactive minerals heats the inside of the Earth. As you go down into the Earth, it gets hotter. And that temperature increases at something like 20 degrees every kilometer, depending on where you are. But if you think about that for a moment, what that means is when you've got down to about 5 or 6 kilometers, temperatures are at about 120 degrees, which we've already said are the upper temperature limit for life. And that means that life doesn't go very deeply. You might think that 5 kilometers is very deep, but here's my technical diagram of the Earth, and here's the Earth here, and this black line that I've drawn with a biro is the extent of life on the Earth. If you go any deeper than this, you're at temperatures well above 122 degrees where life cannot exist. And as you can see, life is a very thin layer. In fact, even this is an exaggeration because my biro wouldn't draw a thinner line. The biosphere is probably about a quarter the width of this line. So life is not everywhere. You'll often hear people saying life is everywhere. Isn't it amazing the way everywhere you look you find life? It's pervasive. Actually, it's not. Life is a very thin layer of material on the surface of the Earth and just beneath the surface, attached to the surface of the planet. And in fact, it would probably be better, rather than calling the Earth's biosphere a biosphere, to call it a biofilm. It's a thin layer of life. And the reason why that's interesting is not just because we learn something about life on our own planet, but we might also suspect that if we went to other planets and life was similarly restricted by high temperature, it would also form a thin layer of material on the surface and just beneath the surface of a planet. So we start to learn things about the universality of life. And I should say that even if you were to imagine some wild alien life form that could grow at much higher temperatures, say 200 degrees or 300 degrees, it doesn't actually increase the thickness of that biofilm that much. So the temperature limits to life tell us something about the extent of life on our own planet and potentially elsewhere in the universe. So what about other extremes? People have looked at low temperatures as well. In fact, it's very difficult to define the low temperature limit for life because, like you and I, when you reduce temperatures, things tend to get a bit sluggish and microbes start to turn over their metabolisms very slowly. It's very difficult practically to measure those things in the laboratory, but we think that the lower temperature limit for life is probably something like minus 25, minus 30 degrees. It might go lower than that, but not that much lower. Below those temperatures, molecules start to work very, very slowly. But if you think about this for a moment, a temperature of about minus 30 or so to 120 degrees or so is a very narrow temperature range in the total temperatures in the known universe. So already we have some idea about how temperature and temperature alone limits the extent of biology on our planet, potentially elsewhere. So what else? Other extremes. Extremes of pH. If you go to the Rio Tinto River in Spain, where the pH is about 1, like battery acid, we find it full of microbes. If you go to Mono Lake in the United States, where the pH is about 13, very alkaline, it's full of microbes. In fact, we do not know of a single environment on the Earth where extremes of pH, acidity or alkalinity, actually prevent life from growing. It's the one example of an extreme that does not seem to limit life on our planet, unlike temperature. In fact, it turns out that life doesn't like acid and alkali inside the cell. The biochemistry tries to maintain a neutral pH. So cells are very good at pumping in and out protons, protons being the basis of acidity and alkalinity. And the cells do their best to try and maintain, in general, a neutral pH. Not in all cells, but most cells maintain a neutral pH. So in that sense, life is not really adapted to acid and alkaline. It doesn't really like it at all, but it is adapted to being able to prevent the biochemistry of the cell from being damaged by these extremes of pH. There are other extremes. Radiation. Radiation is interesting because lots of planets have higher radiation than on the Earth, like the surface of Mars. Can or could, in theory, life grow under these high radiation conditions? Well, it turns out it can. In fact, some microbes can tolerate radiation doses 5,000 times higher than will kill a human being. Deinococcus radiodurans is the strange name that belongs to a microbe that lives in extreme deserts in the world and can tolerate these very high radiation conditions. And it does that by some astonishingly interesting adaptations. For example, it can have multiple copies of its genome or its genetic information, so that if one copy is damaged, the other copy can, so to speak, take up the reins and do the biochemistry instead of the damaged copy. It contains manganese and pigments that can quench, or in other words, destroy reactive free radicals inside the cell. So when you bombard a cell with radiation, you get these reactive states of molecules, free radicals as they're called, that can go around and damage other biological molecules. And cells that can tolerate high radiation have particular pigments that can mop up these damaging reactive states and stop the cell from being destroyed. So we know that life can adapt to higher levels of radiation. What else? Well, high pressure. It may be a slightly strange thought to you, but in fact, most life on Earth lives at a higher pressure than us, either deep in the crust, in that 5 kilometers where we think that life is, but also in the deep oceans where high pressure also prevails. In fact, it turns out that human beings are strange low pressure creatures that live at 1 atmosphere pressure. If you want to think of it like that, most life on the Earth is actually at a higher pressure than us. How does life deal with higher pressures? Well, you may be familiar if you go into the kitchen and squash your food, you can compact it under high pressure. The same thing with many molecules. Some molecules, when you pressurize them, become more compact. And that makes it difficult for food to get into a cell and waste to get out. And cells have come up with some interesting mechanisms through evolution to deal with high pressures. For example, they might have special transporters in their cell membranes that allows food to come in and waste to go out through these compacted cell membranes. Another mechanism is to introduce into the membranes fatty acids that allow for the membrane to maintain fluidity. So although the membrane tends to be very packed up and compact under high pressure, these fluid fatty acids maintain that fluidity and allow the cell to have a little bit of leakiness, if you like, and movement in the membrane that allows molecules to move in and out, and so on and so forth. cells have evolved all sorts of ways to deal with different extremes, and there are other extremes besides. In many natural environments, we find more than one extreme. At the bottom of the ocean, it's high pressure, but it's also cold as well, and microbes have adapted mechanisms to deal with multiple extremes. All of these things give us fascinating insights into how life can survive limits, what the limits to life are, and if we go to other planets, to help us understand whether those environments could theoretically support any life, even if there's no life to actually take advantage of those conditions. Another interesting thing about life in extreme environments is that we can get useful molecules from them. How do you think your biological washing powder works at 60 degrees in your washing machine? It works because it contains biological catalysts, enzymes that were originally extracted from microbes living in volcanic pools. So from these extreme environments, high temperatures, low temperatures, extremes of pH, extremes of pressure, or what else, we can extract molecules that can be useful in industrial processes that we might want to carry out at these extreme conditions for various chemical reasons. But they can also be useful for everyday processes that you and I need, like washing our laundry. So extremophiles, these microbes that live in these extreme conditions, can provide useful molecules of industrial and everyday interest. So that's life in extreme environments, a very fascinating area of microbiology, giving us fundamental insights about life on the Earth, about the limits to life, and also a way to be able to assess the possibility that other planets might be able to support life. Look after yourselves. Thanks a lot for joining me.